Welcome once again. Tonight we're going to talk about the unobservable. That is, you want to go observe something, but for a number of reasons you can't currently observe it from either your location or your date and time, or it's not up for you to see it, but also the things that you cannot observe in the electromagnetic spectrum and how we indirectly look at those same things, because we've only got one mechanism for doing digital observations, and that is the photoelectric effect. So photons creating electrons, counting electrons, doing a digital to analog conversion and go, we've got pixels or we've got numbers. And sometimes you have things like gravity waves that they don't work like that, but we find ways to observe them indirectly. So as I was saying, it's pretty obvious some of the reasons why things may not be observable. The first of which is the physiology of the human eye. Things that get in the way, either transient or permanent obstructions. You're in the wrong place, can't see that from here. The date and time may not be conducive to observing. If you want to observe the sun, better be in the daytime. If you want to observe the moon, it could be in the daytime, could be at night. The target is hard to detect. It's so dim, so far away. I've got to go out to a dark site, or I've got to use a really good deep sky camera to observe it. The target either doesn't produce or reflect photons to the electromagnetic spectrum. It is invisible and we'll detect it through indirect means, or the target emits other than photons like gravity waves or neutrinos, and then we look for this to detect that to say must it be indicating this. So we'll get into details of all of those. Start with human physiology. The human eye cannot see in radio, infrared, ultraviolet, X-ray, gamma, all those sorts of things. Or whatever you can look at that we can detect is too dim. It's not producing enough photons per square area per second or flux for us to see, like, it's too dark, I can't see it. So for those things, we create instruments that takes in the information and then converts it into something we can see. Typically, that's referred to as visual color or false color. But for simple astronomy, we have low light, cooled cameras that we put on our telescopes. There's the Hubble Space Telescope, the HST. It's in low Earth orbit. It can see in infrared, visible, and ultraviolet, although the James Webb Space Telescope can see deeper into infrared. JWST, also known as the Webb, it's in a virtual orbit about Lagrange point 2. It sees in near infrared to not quite the maximum depth of infrared, because that's closer to radio waves, and optical instruments don't see in radio waves. There are ultraviolet imagers that we've actually put on board the old space shuttles, and we flew that a couple of times. That's the HUT. That's the Johns Hopkins Ultraviolet Telescope, the HUT. For X-ray, we have the Chandra, which is in an elliptical geocentric orbit. So it's one of the foci of the ellipse is the Earth, and it's making very long ellipses to get out from the background radiation of the Earth to do its imaging and then come back to do its data transmissions. And then we have the Fermi gamma ray telescope that is in low Earth orbit, because aside from the Earth's atmosphere, gamma rays are just fine even in low Earth orbit. And sometimes we've actually put telescopes in orbit around the Earth, and we did the imaging when the sun was behind us, because the sun is a very large source of various forms of radiation. And if you don't want to be blinded by the sun, you have the sun behind the Earth and you point away from the Earth, and now you can image. So it works even in low Earth orbit. And then you have obstructions, transient obstructions. Oh yes, clouds, and more clouds in South Florida in the summertime. But you can also have fixed obstructions like buildings and trees, and they're just going to be there. And sometimes it's, well, the target I want to see is out in the open part of the sky, but I need to line up on Polaris, and it's currently blocked by a building or a tree. And so move the telescope somewhere else or get yourself an altitude azimuthscope that can be aligned using a GPS receiver. But typically for clouds, we'll just wait until they pass. For other things, it's you've got to move to a different location, like an open dark site or from space. But sometimes, even when you think you've got a dark open site, things go by in the sky that it's cool to pick them up in your image, but if you were looking to image the craters behind that airplane, you got to take more pictures. And your observing site, the target that you want to observe, may not be visible from your most popular site. What you want to see may not be out currently. Or let's say you want to observe the sun, but you're doing it from a very northern or very southern latitude, and that time of the year for 6 months, the sun's too low into the muck of the horizon for good observing. Or certain days of the month, like I want to go observe the moon. Not during the new phase, you won't find it. And even planets. Planets can be out in the morning, planets can be out in the evening. That's where you have the morning and evening stars, nomenclature for them. So you may have to pick when you can see it and get up early or stay up late. Your observing target may be visible, but your alignment target's not. Be it a star pattern if you're doing plate solving, or Polaris if you're doing equatorial or polar alignment. Typically, you can just wait for a different time for that site to observe. And if that lines up, good. If it doesn't line up, come back later. Or you can move to a different site. And here's the one that people always stress about. I want to see an eclipse. Sorry, it's not going to be a total eclipse where you are. It may be a partial eclipse, 25, 30, 50, 70% eclipse. Or it may be, I'm sorry, where you're at, this eclipse is just no C. So it's just the sun. So you either have to move to a different location or wait for a different time of day to see it. And that can happen with solar and lunar eclipses, close conjunctions, and occultations. Occultations are notorious for being, I need to move another mile down the road, or a mile down the road that way, or wait another 5 minutes. Or the target is just hard to detect. It's too dim. There's too few photons striking your eye or your detector in order to be able to see it. And I will absolutely agree there are circumstances where that can happen. But just saying it's too dark to see is too easy and out. There are other ways you can do that. If the target is too small and too far away, not sufficiently reflective, has a low albedo, yeah, we can say that about Planet 9. You can't see it because it's too dim. It's too far away. Maybe you're just not looking in the right spectra, or maybe you're not looking at the right time, or maybe you're looking in the wrong direction. So a lot of times when they go, it's hard to see it. Okay. I don't always buy into that. Maybe different instruments or different sites or different conditions. But we are building different instruments and we're putting them in special places. LIVOIR, which is the light ultraviolet visible orbiting infrared observatory. It's going to be renamed the Sagan telescope, and that's going to be many times larger than the Webb telescope, and it's going to see in a much broader range of spectra than the JWST. And when you think, well, what about seeing the oldest stuff in the universe? They're actually going to be putting, if they get the funding for it, ULFAR, but they're going to look at ultra low radio frequencies. So when you talk about how long a wavelength can I have? Well, if you have an array of lunar orbiting radio telescopes, then you can have some very long interferometry. So you can have very long wavelengths, and we'll be able to see the universe older than the cosmic microwave background, because we'll be looking at the cosmic shortwave background. But shortwave is actually much longer than microwave. We have a singular digital observing mechanism. What that means is everything that we look at is either in film, which is not that popular anymore, or it's in observing in the electromagnetic spectrum, the EM band. And that's where we look for radio, infrared, visible, ultraviolet, X-ray, and even gamma. Not cosmic rays, though, because those are chunks of atoms. They're not really just photons. And we even use that same technique for indirect observations for things we can't see directly. And it's the photoelectric effect. Photons will strike a metal plate inside of a vacuum tube or a metallically doped semiconductor sensor material, causing it to emit electrons. If you have a single pixel, we call that a photometer. If you have a pixel array, we'll call that an imager or a camera. Each one of the measurements of those pixels goes through an analog to digital converter. It takes in the electrons, it counts through a ladder the electrons per sample, and then it reads out as a voltage, and then we can use that as an amplitude measurement from that pixel. Notice I didn't say color. The selection of wavelength of frequency of the photon is in the chemistry of the sensor. There's no value we can read out that says that's the frequency of it. In order to flip it and take the amplitude and calculate the frequency, we use something called a fast Fourier transform. But everything that we capture is in grayscale, and even when you see color, we're just taking filters, receiving a different grayscale, and then post-processing the result and mapping colors or creating false colors. And sometimes we have to look in other wavelengths because the thing we actually want to see, you can't directly detect. This is a particular dramatic example of what is to be built for detecting Cherenkov radiation. And that's from muons in the upper atmosphere being struck by neutrinos and producing a particular wavelength of light. And what they're doing is they're receiving the muons, and then that big white square up at the top center of each of the telescopes actually takes the muons in, converts them to electrons, produces photons of a particular blue light, Cherenkov radiation, and then it converts the photons back to electrons in order to make the measurements. So it's a lot of roundabout with indirect measurements. And there's other indirect things that we can do. When you look at something and you're continually taking images of it, and you notice there's a distortion in the image. So if you're snapping background stars and you do that often enough, and you notice that the stars go from bright to dim to bright, that's because something's going in front of the stars that you can't directly see. So you'll measure the inverted brightness of it by how dark the star gets. Or the really weird one is something called frame dragging, where you'll see a distortion fan out across other things. It didn't actually occult a particular star. It affected other stars by the frame dragging due to the gravity of that thing moving through the field. And if you have something that's behind high gravitational objects, it can actually bend the light around and show you multiple images of it. This is called an Einstein cross or gravitational lensing. So even when we can't directly see something, if we can find its effect indirectly, we can observe in the electromagnetic spectrum indirectly. Well, what about for things that don't involve photons? We'll find a way to involve photons even when it doesn't involve photons. So you've known about gravity waves. We indirectly detect these with interferometers. And the initial LIGO and Virgo observatories here in the US, they can only observe high amplitude, low frequency gravitational wave sources up to about 10 kilohertz. Well, what if it's higher than that? They're blind to it. What if it's really low, like well less than 1 kilohertz? They're blind to that. So they've got to improve the gravity wave detectors, probably through advancements in things other than interferometry in order to pick it up. But they need to do even better. And in the next slide, I'll show you what they're missing. But this is indirect observation. We can't actually see the gravity waves, but we can see the stretching of the fabric of space-time versus the light beam from the laser that we're shooting through it. So as it stretches and then we merge the light together, we get a distortion field. It's either destructive or constructive wave interactions. And if it's destructive, we see nothing. That's the normal state. But the moment one of the two arms stretches, that becomes constructive, and it produces something we can detect with photons. They found out recently that the Fermi Gamma Ray Space Telescope can actually detect gravity waves because there are constant gamma sources in space. And if you notice that the gamma source wavelength wiggles, that's because the space that the gamma radiation is going through was involved in a stretching due to a gravity wave. The other thing that we do for much larger areas is we have 100 plus pulsars that we measure their timing down to the microsecond level. And when you notice that all the pulsars over in that part of the sky suddenly had their timing shift by microseconds, it's because there's a gravity wave flowing through that part of space. So we're looking at different ways to do indirect detection of gravity waves. There's two instruments that they're working on at Fermi Labs. One is called Magus 100, and this is a evacuated vertical drop tube that's 100 meters tall, 300 feet deep. And what they're going to do is they've got an object, and the object puts out a particular set of emissions. And if they drop it through the tube, and if a gravity wave comes through, it will change the difference between what it records and what you can record from it. So you'll see a delta, so it'll be an indirect detection. But you can only detect it when things are dropping through it, so it's not continuous. And DUNE is for looking at neutrinos, and they're actually going to be shooting a neutrino beam through the mantle of the Earth, because the neutrinos will pass right through, and they'll detect them in detectors hundreds of miles away. So indirect detection is growing in popularity. Well, we can't see this, but we can see that. If that's an indication of this, then we know that happened. So here's how you know when you're missing more. So this is one of the gravity wave detections from LIGO and Virgo. And I blew it up so you can see there's three of these green rectangles around the signal. If you look to the left edge of the signal before it starts getting detected, you'll see a little bit of wave there. But that's the level of amplitude it can detect. There may be even lower levels of amplitude that precede it that it cannot detect. And the next one over, you'll see the wave going through, but if you look closely, there's a background image behind that wave that the original waveform is this like really ripply blur. That's because the sample rate is too low, and therefore it can't see all the crests and the valleys of the particular frequency that's going through. So you have an amplitude that's lower than the sensor's sensitivity, and you have a sample rate that is too slow for the changes that, Nyquist guy. You need twice the frequency in order to sample to detect something. So there's that. And then the one over on the right side is, well, when it gets too low an amplitude after it's gone through, we don't know how long the gravity wave actually rings. We can see like it gets to a high peak and then it tapers off. But there's stuff on the right side that we can't measure. And we know it's there because we can see it in the signal. At what point does it taper off to nothing? Our sensor can't detect that level. So there's room to go. And if you want an analog scenario, think of how long did we not know that elephants communicate in infrasonic communications? This is audio that penetrates the ground for what could be dozens of miles, that the elephants can talk to each other. Well, we can't hear it because it's infrasonic. It's below our human ear's ability to detect that sound. And we actually use that for submarine communication. We communicate with submarines using extremely low frequency radio that penetrates the crust of the earth. It's very low data rate, but extremely low frequency is something that whales are susceptible to, and it causes their ears to bleed. So we could be killing whales by intense low frequency radiation that we beam through the mantle of the earth. So there's a concern for, should we be doing this? Well, we only use the ELF when it's a government notification of like, here's what you do with your nuclear weapons. So we don't use it for regular communications because, yes, it harms wildlife and it's very, very low data rate. So you're not going to be doing a lot of signaling that way. But we got it if we need it. And this is my favorite one. The philosophically unobservable. What we don't wish to see, we find ways to make it not observable. And if we can't ever see it, we never record an observation of it, presto, it's not there. This is the infamous gorilla or elephant in the room. If you don't talk about it, it's not there. It gives you plausible deniability. You know, if you've never asked, you never need to admit you detected it. We won't say we observed it because the thing that observed it or what you're observing is some black project. So much like the latest UAP works, it's, okay, anything that we observe, that we have evidence it exists, but it's a black project, we just kind of extract that from the available data and can't see it, never happened, plausible deniability. But if we really wanted to see these things, employ better detectors, employ more detectors, mass deploy observing instruments. We can create those because it might see something we don't want you to see. Why not use all those traffic monitoring cameras and environmental monitoring cameras to detect things you can't otherwise see? And even when we see things, we know what happened given those instruments. We don't ask for, oh yeah, and what happened with the other instruments? So we'll ask about the fighter jets that have infrared or nose camera images of some UAP, but that was during a fleet maneuver. What about all the other aircraft and vessels of the fleet? What did they record? If we don't ask, then we don't have to explain why we actually detected something. So it's philosophically unobservable because we never asked. Don't ask, no reason to tell. The one that always gets me is when we say, well, we can't say we actually detected that because we just didn't send the right kind of instrument to detect that positively. So when we go to Mars and we say, we kind of sent the right sensors to detect life, but if that life happens to be too sophisticated, we didn't send the right sensors. So if we're looking for some thing that might be producing a gas, like, you know, it takes in sunlight and produces, I don't know, oxygen, like photosynthesis, we can't detect that because we didn't send the right kind of sensors. We'll do that next time. Trust us. But if you never want to see that, if you never want to detect that, then make sure that your spacecraft never has the proper instruments to detect it. Or even if you do have the proper instruments, like on Mars or in the upper atmosphere of Venus, detecting signs of biology. And no, that's not, basically ignore the elephant in the room. We know we officially detected particular biological activities that are rare in nature and common in inhabitable places, but no, we didn't see that. Okay. So in conclusion, observing is a wider concept than just seeing something. Humans see only so much of the electromagnetic spectrum using eyes. We create instruments to take us beyond our physiologic limits. If something obstructs us, we'll find ways to get around it. We'll move or wait or whatever. Sometimes we have to be in the right place at the right time for things like eclipses and occultations. Sometimes we can only observe indirectly because either the target doesn't produce enough photons or doesn't produce photons at all, like gravity waves and neutrinos. We have a singular mechanism for doing digital observation, and that's just photons making electrons going through a digital converter, and we have digital data. And sometimes we won't observe what we don't want to see, or we don't equip craft with the instruments that would provide conclusive evidence. It's just indirect evidence or hearsay evidence. And then, as usual, a bunch of links. Comments, questions?
Very nice.
Yes.
I have a comment, a question. It's a question comment.
Go for it.
Conspiracists would like this video, I think.
Only the last slide.
Okay.
Yeah. And I have seen, Viking observations and curiosity observations, and the instruments that they send do have the ability to detect things that are predominantly generated by biologic actions. They are generated in nature only very rarely. You have to really stretch to detect it at that level from geologic activity. So, yeah, if you never want the answer, never ask the question.
But then again, why wouldn't we want to see certain things? Things
in our atmosphere are more like, if you could see all that's there, you might see some black projects that we don't want you to know are there. So, yeah, we don't want you looking.
So certain.
But in the case of stuff on other planets, imagine the paradigm shift if all of a sudden they came back and said, we've actually found biological live material on the surface of Mars. We lifted up a rock and there was algae. It was maybe blue-green algae because it had to survive under harsh conditions, but that exists on Earth. Helen and I saw some of this stuff at Yellowstone, where you go to the highest altitudes in Yellowstone and you look and there's all sorts of lichen in different colors. And what are they feeding off of? High energy photons and water.
Amazing.
They're surviving, they're thriving like crazy.
Yeah,
So
that's what we named extremophiles.
Yes.
Yeah.
On the Earth, we have extremophiles, but there are extremophiles that don't have
Compared
to be that
to our-
extreme. Compared to humans, they're extremophiles. But to compare them to other things on the Earth, when you see,
They are majority of it.
yes, when you see shrimp hovering around a volcanic vent several thousand feet under the sea, those are not like really exotic, bizarre shrimp. Those are shrimp. When you see lichen surviving in ultraviolet radiation above 10,000 feet where the air's thin, those are real, and there's a lot more of that than there are humans on the planet. So,
Right. But then this is so interesting. We want to see it. No.
well, we, the public, want to see.
Yeah.
If you're looking for life on another planet, they don't want you to find it because it's gonna contradict their secret books of whatever mythology they believe in. You have the technology to see beyond your imagination. In 60 years, our technology changed so much that we have those instruments in the palm of our hands and we are not looking up.
Well, I think science will prevail. Politicians have certain limitations.
I think it will be very much like amateur astronomy. Amateur astronomers are the ones that are predominantly looking up all the time and are finding minor planets. They're finding asteroids, they're finding
Exactly.
comets. It's because they have the technologically sufficiently advanced instruments to see these things.
And
And
the interest.
I think the same
And the interest. There you are.
and the desire to do it and the wallet to do it. So I think the same thing's going to happen with UAPs. Eventually, we're going to have undeniable evidence of whatever those things are, and we're going to find out they be us. You know, they're going to be Black Project stuff, because all the most concrete evidence that we have for whatever they are is offshore. You know, it's on the west coast of California, out at sea where they were doing naval maneuvers, or it's way off the east coast of the U.S. where they're doing naval maneuvers, or it's way above Alaska at the north end of Canada where nobody else can see it. So the moment these things start flying over regular areas and we start having the instrumentation quality, you know, we get out to like 8K and we're doing infrared in 8K, that's going to make it very difficult for them to hide. But there are observational techniques that we haven't even broached the advancements in technology. If you can observe in radio the cosmic background radiation, and you observe in radio, it doesn't matter whether you have stealthy radar absorbing or reflecting or whatever, you're going to see the hole where the thing is. That's like frame dragging. You can't see the object, but you can see the frame drag effect. Technology is going to get to the point where it'll be unpoliceable because you're not transmitting, you're receiving, and you're receiving a background source of illumination that is available and unstoppable in nature. So if you work with indirect observation using available light sources that are ever present, you're going to see things that otherwise wouldn't be detectable. And once you have that, and a lot of people have that, it's going to be undeniable. If you look at the last UAP report they put out, they said, we're going to ignore all the information from that group of technology-minded people that did legitimate scientific observation because it's only one source. We didn't have multiple sources. You had multiple sightings, you had multiple observing locations, but because it all came in through one company source, you're going to discard all of it. That's just bogus.
Yeah, that is.
But, or as the saying goes, until you have a lot of people outside the White House and it lands on the White House lawn and walks over and says, I'd like to speak to the president, please, it won't be real. Or the people that are really extreme and say, until it lands on my front doorstep, I won't believe it exists. They're probably also the ones that believe in a flat earth and we never went to the moon.
Yeah, that's what is funny. That whatever is has lots of evidence, has, research behind it, and people saying and that, oh, I don't believe it. But then they read one article saying something preposterous about something ridiculous, and they believe it in 1 second. I don't get it.
That's the thing all along. Go through the last, let's say, 100 years of our human history.
Yes.
You find this all over, all the time. The most absurd things are taken for real.
Well, when they'll say things like, I know the earth is flat, I read it on the internet on my mobile phone.
Right.
Do you know where you are right now? Yeah. Google Maps shows me right where I am. The flat earth Google Maps. Yeah. So we're talking speed of light, that's a problem. We're talking a globe that has satellites orbiting it, that's a problem. But you still believe the earth is flat. Yeah, I saw it right here on my mobile phone. Okay.
This is like the technology they use to disprove it, that whatever they want to disprove is the technology that works with the science that proves the opposite. It's like, oh my goodness.
Yep.
Yeah,
Don't
but that's
argue
part
with the
of
brick. Don't argue with the brick wall.
Yeah.
Yeah, I think that's so much a part of human character, which I found unbelievable. Yeah, so James Randi used to say that, right, Monroe?
Yes.
I mean, when I started going to the meetings that he would have, and I'd say, well, surely people are going to see this and believe this stuff, and
Oh, can't see it.
be able to use it. And he says, no, they're never going to see it, no matter what you show them. And in particular, he had those TV series, right, where
Yep.
he'd show you clearly, like with the what's it called, dowsing for water, and
Yes.
he 12 covered containers, and nobody could ever do it. And yet the shows would go out of business because people weren't even interested in watching the things be
Yep.
disproved.
I think it's just,
Is that what you were saying, that we don't want to see it?
no, I think it's a matter of we are extremely programmable and pliable. And once we get locked onto something, it's very hard to change our programming.
Yeah, that's the worst part.
Mhm.
And I try to be aware of this for myself.
Well, that's why I point out that science has a problem like archaeology. If they find something that's 15,000 years old, that's a socially ordered city, it's going to be real hard for them to say, we didn't exist until here. Yeah, that's a paradigm shift.
Yeah.
Or we're the only thing in the universe. And then somebody arrives and goes, hi, we're here. We look just like you. We speak just like you. But we know a lot more about how the universe works than you. That'd be a massive paradigm shift. So
Yeah.
I'm just waiting for them to happen. I've seen so many paradigm shifts in technology that we just don't even think about when they happen anymore.
No. We
Um,
just go in line in front of the store to buy
mean,
one a new.
We've endured, as a species, we've endured massive paradigm shifts. We create major cities. We had horses everywhere, but then the manure got to be too much of a problem. No more horses. Except for pleasure, people would buy horses and still ride them, and that was fine. Even when it's a massive paradigm shift, it doesn't need to convert everything. They can still coexist. They just exist at different levels. When you can prove something in a cyclotron or a linear accelerator, and you can do it repeatedly again and again and again, it's kind of matter of fact. But when you come up with something that you can't prove, the evidence is still out.
In a way, but we are taught in higher education that we learn how to do our research to find things. Of course, it's not being taught in school,
Right.
but we have to do our research ourselves.
Yeah.
And that's the thing, is we have a society that is making sure that individuals no longer have the capacity to do research, no longer have a desire to do research. This is what I was taught in school, and the end stops there.
All right. But that's we were taught when you finish school, that's the beginning
Yes,
when you really have to learn.
yes. High school is the last time you're supposed to learn it. That's the way it is. Just accept it. When you get into your baccalaureate degree, you're supposed to be provided with the tools
The
to
tools.
learn what you don't know or learn what didn't exist yesterday.
Right. That's what we were told in the
Yes.
end. Now you're in the beginning. Here
Yeah.
are your tools.
Yes. A master's degree is to teach you how to report on things. I
Right.
researched it. It's now new science. I can write a report on it. I can publish that. And then your doctorate degree is to take that report and actually educate other people about it, to pass on your knowledge. That's why, typically somebody with a doctorate will wind up being a teacher at a university, because that's what your doctorate is supposed to give you the capability of doing. Not only learn what you know, repeat it, research what you don't know, write material on what you don't know that's new stuff, and then educate others about it.
Right. That's it.
Yeah.
Sounds so simple.
There's a reason why higher education exists. And for the people that say, who needs a college education? I will agree that there are some people that a college education isn't appropriate for them, but there are other people that until you realize the value of it, why would you deny people that ability? And the answer is money, money, money. Because if I can make a public college education so expensive that very few people will be able to afford a baccalaureate degree, I've just dumbed down society.
Right. That's
I've
the
cre-
idea. Yeah.
I've created a society of welcome to Walmart. The fact that something is inaccessible to the masses does not mean that with a little effort, it's inaccessible to the masses.
All right. Cinderella time.
Right.
We're past pumpkin time, so
That's it.
any comments or questions before we close? Next week we'll talk about quantum foam power generation. Okay. Enough for tonight.
Right. Thanks so much. Stay well.
Bye, everyone.
Thank you.
Next
Have a
time.
good night.
Good night. Thank you. Bye-bye.
Good night, everybody.
Good night. Thank
I'm
you.
in Walmart for the plow.
Bye-bye.
Bye.